Good day, viewers. My name is Ode Godwin Daniel, and I'm your tutor. Please do well to subscribe and follow us across our social media pages at Godwin School of Mathematics. In our last class, we started a series of teaching on set theory. And then we learned that set theory is a study of set and everything that pertains to set, while set is a collection of well-defined objects or group of objects. And then we said these objects are called elements or members of the set. These elements or members are enclosed in a curly bracket called set bracket and are separated by a comma. And then we say a set is represented using capital letter, while the elements of the set are represented using small letters, numbers, or symbols. Today, we'll be looking at the representation of sets. Now, the representation of sets are the ways in which we represent the elements of a set, how the elements of a set are given. There are two ways or two representations of a set. Number one, we have the roster form. Number one, the roster form, also known as the listing method. The roster form or the listing method is a representation of sets in which the elements of the set are listed or the elements of the set are given. For example, we have the set A is equal to A, E, I, O, U. Now, we already know that the elements of A are A, E, I, O-U. Why? Because they were given. Why? Because they were listed. Another way of representing the elements of a set, number two, is by set builder form. Now, the set builder form is unlike the listing method or the roster form. Now, the elements of the set are not listed. Rather, the elements are given certain properties for you to crack out, for you to decode. Now, in you properly decoding these properties, you are now able to list out the elements of a set. For example, we say the set B is equal to the set of X such that X is an element of the set of natural number, and then we say minus 2 is less than X, X is less than 8, right? Now, if you look at these properties given to the set B, B is equal to the set of all X. Now, the elements of the set B are given a variable, say X. Now, X is further defined to say X is an element of the set of natural number. Now, these two dots in set simply means such that. So if you're going to pronounce this, we say B is equal to the set of all X such that X is an element of the set of natural number. Now, this symbol means element of or member of or belonging to. So you can use any of these words to say B is equal to the set of all X such that X is an element of the set of natural number, or you can say X is a member of the set of natural number, or you can as well say X is belonging to the set of natural number, right? And then X is then further given property to say minus 2 is less than X, while X is less than 8. So if you are able to decode this, we can get the elements of 8, but we are not done yet. We're also told that X must also be a member of the set of natural number. First, what is the set of natural number? Right? The set of natural numbers is a set of counting numbers. So when we start learning how to count numbers in our nursery school, we started by saying 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the set of natural numbers are the set of counting numbers, which is equal to 1, 2, 3, 4, 5, ellipses. Now, these three dots means ellipses. It's called ellipses, and it means continuous on. It means that the listing of these elements is continuous on the same order the listing started and is given. And was given. So we have after 1, 2, after 2, 3, after 3, 4, after 4, 5. It simply means that this listing is continuous on this same order. So after 5, 6, after 6, 7, 8, 9, 10, 11, 12, up until infinity, right? So the set of natural numbers are the set of counting numbers. We have other set of numbers. We have set of whole numbers, right? So the set of whole numbers are the set of counting numbers and zero. Now, set of natural numbers are the set of counting numbers. That is 1, 2, 3, 4, 5, 6. Right? While the set of whole numbers are the set of counting numbers and zero inclusive. So we say that the set of whole numbers is equal to zero inclusive. 1, 2, 3, 4, 5, and continuous on. Right? And then we also have set of integers. The set of integers, right, is the set of positive counting numbers and now the negative counting numbers and zero inclusive. So we have ellipses, right? -4, -3, -2, -1, 0, 1, 2, 3, right? Ellipses. It's continuous. Then we have the set of rational number. The set of rational number is the set of numbers that can be expressed in form of fraction. That is, any number that can be expressed to have a numerator and to have a denominator. That is, a number that can be expressed as a ratio of another number. For example, 2 is a rational number because 2 can be expressed as 2/1. Right? So 2 becomes the numerator and then 1 becomes the denominator, right? So 2 is a rational number as well as -4, which is the same thing as -4/1, right? So -4 becomes the numerator while 1 becomes the denominator. What does that simply mean? It means that all elements of the set of natural numbers are also set of rational numbers because they can be expressed in form of fraction to have a numerator and the denominator. They can be expressed as ratio of 1. That is 2 to ratio 1, 3 to ratio 1, 4 to ratio 1. All right? Any number that can be expressed as a ratio of another number is a set of rational number, as well as the set of whole numbers are also what set of rational number. For example, 0/1 is equal to 0. So which gives us 0 as the numerator and 1 as the denominator. So, and all of 1, 2, 3, 4 up to infinity, as well as the set of integer, the negative counting numbers, 0, and the positive counting numbers. So every number that can be expressed in the form of fraction is a rational number. Now, we have set of irrational numbers, right? Any number that cannot be expressed in form of fraction, right, is called a set of what? Irrational numbers. Example, we have pi, right? Pi. The square root of every non-perfect square. For example, root 2, root 3, root 5, root 6, and so on and so forth. Also, the cube root of every non-perfect cube is also a set of irrational number. For example, the cube root of 2, the cube root of 3, the cube root of 4, and so on and so forth. And then, of course, it continues. And finally, we have the set of real numbers. The set of real numbers is equal to the set of every other numbers under consideration. That is, the set of real numbers consists of the elements of the set of natural numbers, the set of whole numbers, the set of integers, the set of rational numbers, and the set of irrational numbers. So the set of real numbers comprise of every of them, whole numbers, integers, rational numbers, and irrational numbers. All of them are called real numbers. Now, let's get back to our question. We said B is equal to the set of all x such that x is an element of the natural number, and then we say minus 2 is less than x is less than 8, right? The first thing is to decode this. Having decoded this, we then confirm which of the elements are set of natural numbers. So we have minus 2 less than x. If minus 2 is less than x, it simply means that x is greater than minus 2 and below. If minus 2 is less than x, it simply means that minus 3 is also less than x. Minus 4 is also less than x. Minus 5 is also less than x. Minus 6 is also less than x up to infinity. All numbers from minus infinity down up to minus 2 are less than x, which means that our x begins from what? Minus 1. So we have minus 1, 0, 1, 2, 3, 4, 5, 6, and 7, because we're told that x is not up to 8. X is less than 8. So every number from 8 and above are greater than x, which means our x stops at 7. Now, we can't call all these the elements of the set of B. Why? Because we still need to verify this property that was given. We were told that, so we've been able to decode this. Our x is equal to minus 1, 0, 1, 2, 3, 4, 5, 6, 7. But we were then told that x is also a member of the set of natural number. Now, out of all these elements of x, which of them is a set of natural number? So we say B is equal to the set of minus 1 is not a member of the set of natural number. 0 is not a member of the set of natural number. So it means that our x, which is the element for B, is equal to what? 1, 2, 3, 4, 5, 6, and 7. Right? So the elements of the set were not listed, but were given certain properties such that if properly decoded, you will be able to list out the elements of a set. So we have two ways of representing a set. Number one, the roster form, which is also the listing method. This is the representation of the elements of the set, whereby the elements are listed. And number two, the set builder form, or the set builder notation, such that the elements of the set are not listed, but are given certain properties that if you are able to decode, you will be able to write out the elements of the set yourself. Finally, before we end today's class, let's look at what cardinality of a set means. The cardinality of a set, say A, right, denoted by n of A, right, is the total number of elements in that set. So if you are asked to find the cardinality of any set, what you are asked to find is how many elements are in that set. For example, I have A is equal to the set of 0, 1, 2, 3, 4, and 5, right? And then they said, find the cardinality of A. The cardinality of A, denoted by n of A, is equal to how many elements are in the set A? 1, 2, 3, 4, 5, 6. So the cardinality of A, which is denoted by n of A, is equal to what? 6. So when you are asked to find the cardinality of any set, say A or B, the cardinality of the set B, denoted by n of B, is what? The total number of elements in the set B. Alright. Thank you for joining the class today. I'll see you in our next class. In our next class, we'll be looking at types of sets. We have about 9 types of set. Number 1, we have finite set. Number 2, we have infinite set. Number 3, we have empty set. Number 4, we have singleton set. Number 5, we have equal set. Number 6, we have equivalent set. Number 7, we have subset. Number 8, we have power set. And number 9, we have universal set. Thank you for joining the class, and I'll see you in the next class.